So the most complicated derivative thing that we had was probably the chain rule. You could say the product and the quotient rule were about the same. But what we're going to do right now is learn how to work backwards from the chain rule and how to recognize something was originally a chain rule and then work backwards from that. So what we're going to be looking for is, while we're integrating, we're going to be looking for a derivative inside of the function that we have. Here's one of the examples that we did before. So if you were working backwards, the idea here is we notice two functions. I'm going to highlight this one in yellow and this one in green. And the yellow one and the green one are related because one is the derivative of the other one. And if we think back to the chain rule, so in other words, if we write out what this was originally, this function originally was this, what would you do? You would bring the 5 out in front and subtract 1 from the exponent and keep the inside the same. That inside is what I highlighted in yellow. And then after that, you would multiply by the derivative of the inside. Of course, if we were working backwards, we'd also have to say, oh, it could have plus c here at the end, because it could be any function. So what happens in a chain rule is something stays the same. In this case, what's inside the function stays the same to begin with, and then you multiply by the derivative afterwards. So in order to recognize that it was a chain rule to begin with, we have to be able to see, I have a function that stayed the same, and I have a derivative of that function in the same one. So that's the recognition part, to see one function and its derivative in the same thing. So as a start out here, we're just going to highlight things. We're going to highlight where we see a function and where we see its derivative. So as far as our highlighter goes, we're going to highlight the function in yellow and where we see its derivative in green. And usually, that original function is going to be inside of another function. So in this first one, x squared minus 7 is a function, and 2x is the derivative. And you might ask, well, why didn't I just highlight the x squared? Why did I highlight the extra minus 7? Because the derivative of x squared is 2x, but the derivative of x squared minus 7 is also just 2x. So another thing that happens here is when we're working with the chain rule always had a function inside of another function. So when I'm highlighting my original function, the x squared minus 7, you notice that's inside the power of 4? It's not just the x squared that's inside the power of 4. So we're looking for an entire function inside something else, and then its derivative. So for the second one, we notice that we have this 5 minus 2x to the 4 inside of a square root on the bottom of a fraction. And the derivative of negative of that would be a negative 8x cubed. So over here, I've written the same thing here. And on this side, I've got the derivative perfectly. But what's going to happen when you do functions is you're going to simplify. So if you had this as your question on the right, and you had a negative 1/8 and a negative 8, you would simplify them and just get 1. So another thing that we're going to look for when we're working backwards from the chain rule is we are not going to concern ourselves too much about the numbers in front, the coefficients. We're just looking at the general functions. What's the derivative of an x to the 4 function? It's an x cubed function. So even though the numbers are gone, we can still recognize this is my original function inside of something else, and its derivative will be an x cubed. Because if you had that, if you wanted to get it exact like we have here, you could do that by just playing around with the numbers to make it work. If I wanted a negative 8 out in front, I could put it there as long as I divide by a negative 8 to cancel it out. But we're going to learn techniques that'll not require us to do guess and check or a bunch of like fiddling and trying over and over and over again. We're going to learn techniques to do this so that it works out nice and hopefully not too difficult. But this is going to be considered the hardest integration that we're going to do in this unit. Now this next example, 5e to the sine x and cos x, you kind of have a decision to make. Because the derivative of sine is cos and the derivative of cos is sine, you know, one of them will have a negative and the other will stay positive. But which is going to be the original function and which is going to be the derivative? And again, just like we've done in all these other examples, all of our other ones that we've highlighted in yellow, we're always looking for our original function is inside of another function. So in this one, can you see that the sine x, whoops, that's not yellow. Can you see that the sine x is inside of the function e to the x? And that the derivative of sine is cos, and that cos isn't inside of another function. Cos 3e to the x times 3e to the x, well, our function, the derivative of e to the x stays the same, but that's the one that's inside of another function. And its derivative, which is 3e to the x, is right there outside of the function. So again, we're not only looking for which function is inside of another function, but also what's the derivative. The last one here, it could be, since neither one of these is inside of another function, you could choose either one to be yellow and green. And when we actually do that last one, we're going to find some interesting things can happen with it. Just going to the column on the right, here we have the natural log of x inside of a power function. And the derivative of that is 1 over x. Here's a function on the bottom of a fraction, and its derivative is right there. And finally, this last one, which is missing. There's tan x is inside of sine, and the derivative of tan is secant squared. That one's missing a dx. So part of integration by substitution is being able to look at something you want to integrate and just taking the time to say, do I recognize a function inside of another function and its derivative present at the same time? And the ones that are hard are going to be ones like this one, where the derivative is negative 8x cubed, but we just see the x cubed. So the coefficients aren't going to matter if they're there or not. We just have to have the general idea of the derivative. All right, now this is formal notation. You're not going to worry about it too much. I'll highlight it so that you can see it better. What we were doing before is you're looking for a function inside of another function and also have its derivative present. Okay? And then what we're going to do in this case is we're going to substitute something for that function. And what we're going to do by substituting it for that function is we're going to change our complicated integral into something that looks simpler. I hope when you see that these two are equal, that the one on the right looks simpler. It's just one function and one derivative. So what does that mean for our first example? Well, if we remember what we highlighted in this first example, we had highlighted the x squared minus 7 as the function inside, and its derivative was present here with the 2x. So integration by substitution is exactly what it sounds like. We are going to substitute something in temporarily, and then that's going to allow us to integrate easier, and then we can substitute back at the end to write out our final answer. Even though you might be able to see right away what this one is, because this is a straightforward working backwards one. If you had just done the chain rule, you'd be able to say, oh, I need to add 1 to the exponent and blah, 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 and work from there. But the way that we're going to set this up is we're going to let u equal that function inside, x squared minus 7. Then the derivative with respect to x is 2x. As far as our substitution goes, what we're going to do, and we use Leibniz notation for this, is if I wanted to just get du, I could multiply both sides by dx, and then du would equal 2x dx. Now I'm going to go back to my original function here, and I'm going to rewrite it. Instead of writing x squared minus 7, I'm going to write u. So here I would have u to the power 4, and instead of writing 2x dx, I can now write du instead. And this is a really easy integral to do. Because it's a power rule, what are you going to do? You're going to add 1 to your exponent and divide by that number, plus c. So then you can substitute back. Our u was x squared minus 7 to the power of 5 divided by 5 plus c. If you want to check, we could do the derivative. The derivative of the 5 would come out in front, cancel out with a 5, subtract 1 from the exponent, and then multiply by the derivative inside, and you would get exactly what we started with. Yes? So how did I get the u to the 4? I'm going to just scroll back up so we can see the original equation. I'm going from here to here. The yellow part is u. Okay? So I changed that to a u. I still have that yellow part is to the power 4, so I write u to the power 4. And then the green part, the 2x dx, that's now equal to du. So instead of having something complicated that I have to integrate with respect to x, I change it to something simple that I have to integrate with respect to u. And then once you've integrated that simple function, you can go back and substitute back in. On your question, I have an extra 6 here. I'm just checking. Does yours have a 6 instead of the 4? It does. Okay. So 4 is gone. And there's a 6 in there instead. Perfect. Okay. So again, just to highlight it the same way we did before, we have to recognize that the derivative of the natural log of x is 1 over x. So we let u equal the natural log of x, then du dx is equal to 1 over x so du is going to be 1 over x dx. Now I can substitute that back in. Instead of the natural log, I can write u. It's to the power 6. This x to the minus 1 dx is now just du. And now we have a much simpler function to integrate. Add 1 to the exponent. Divide by that number plus c. And now we can substitute back in. So it allows you to think of your integration rules in a simpler way. You might, if you just tried to do this one directly, and some of you probably could, there is the problem of trying to just grasp all the things you have to do. I have to remember to divide by 7 when I add 1 to the exponent, and I got to remember what's my chain rule and where it's all going to work. And having that much data in your head at one time, especially when the coefficients in front, once we start playing with them, that they're not nice, will cause you to just make mistakes. So what the substitution does is it breaks it down into something simpler. You can work with one simple thing at a time and then substitute back at the end. And here's the great example of where that happens. Because the derivative, if we make u the function inside, which is 5 minus 2x to the 4, then your derivative is negative 8x cubed. Once you work with these a little bit faster, you'll probably just put the du and the dx on the sides like that. Now, when I want to substitute something in, this, as it looks right here, does not show up in my equation. I have no negative 8. I just have x cubed dx. If I wanted just x cubed dx, which is what appears in my equation, what would I have to do? I'd have to divide both sides by negative 8. In other words, I'd have 1 over negative 8 du. Now I'm going to take an extra step here with the substitution just to keep things cleaner. You can probably do this in one step, but just to watch it, what I'm going to do is I'm going to change this to 1 over the square root of 5 minus 2x to the 4 multiplied by x cubed dx. Are you okay with that? Because that x cubed is in the top of our fraction, so I could just have it multiplied afterwards. So now, first substitution, I would have 1 over the square root of u, and then here I'd have negative 1/8 du. This still doesn't look very neat, the way that it's set up. It doesn't tend to be something that you could easily do a power rule for, so we're going to need to change our square root to an exponent and move it from the bottom to the top. Other things that we learned about integrals is whenever you're multiplying inside by a number, like negative 1/8, that negative 1/8 could come out in front of your fraction. So I'm going to bring the negative 1/8 out in front of my integral. I'm going to change my square root of u to u to the negative 1/2, and then I just have du in there. Now integrating this is easy. We're going to add 1 to the exponent and divide by that number plus c. Mental math with fractions. What is my fraction in front going to be in the end? If I have a negative 1/8 in front and then my next fraction is dividing by a half? Negative 1/4. And then u, we know that to be, what was it again? 5 minus 2x to the 4. To the 1/2 plus c. This would be an example where if you tried to do it directly, there's just so many things involved. Fractions, and the derivative doesn't quite match. Too much involved that the substitution really breaks it down easier. Still is not an easy substitution question, especially because originally what we have in the box here, the negative 8x cubed dx, didn't match with something that was in the equation. You had to divide by negative 8 to get just x cubed dx. But then once you substitute it back in, you had something easier that you could integrate and then substitute back at the end to get your final answer. Okay, I'm going to let you try this one. Go over the answer in a bit. All right, so to start off with, we're going to let u equals sine x, then the derivative is cos x dx. Your integral becomes 5e to the u du. Integrating e to the u, it stays the same, plus c, substitute back, and we get 5e to the sine x plus c. What happened to du right here? Okay, so what this du and what this dx mean in the integral is they're telling you which variable you're integrating with. Just like sometimes in our related rate problems, we took the derivative with respect to time. And sometimes we take the derivative with respect to x. So you choose which variable you're integrating for. Yeah, and because this is a u and this is a u, it's straightforward, right? Because this is x and everything here is x's, it's straightforward. Where things get complicated is if it would say, do the derivative with respect to x, and everything here is in t's. So then you have to find out what's the function of t with respect to x and substitute everything back, and it would be more complicated. But as long as the du matches the variables that are there, you can just do it, we'll say, like normal. In other words, you don't have to worry about it. But if this was du and all of these were x's, then you'd have to be, then we have to do some substitution. And that's what our substitution does, is it changes your variables. And it makes something more simplistic to integrate. I like this one. Okay, so let u, again, we have to recognize that this function, its derivative is present in the equation. And so when we substitute, we get 1 over u du. How do you integrate 1 over u? It's the natural log. Plus c. Now, again, what I really like about this question is when you look at the original question, you probably did not have a gut feeling, oh, natural log. Totally looks like, doesn't that? Totally looks like a natural log, that original equation. No, because the way that it's written doesn't appear like a natural log at all. But once you do the substitution, you get the 1 over u, and you're like, oh, there's my natural log, derivative of my natural log. And it's that much easier. Unless you're not recognizing derivatives of natural logs at all yet, then you just need to do some more practice. But the substitution helps you see what kind of integration you need to do a lot easier. And I'll let you try this one. So here the function inside is 3e to the x, and the derivative of that is 3e to the x. So substituting back in just gives you cos u du. Integrating cos, positive or negative sign? Positive. Because the derivative of sine is positive cos. So working backwards, cos will go back to positive sine plus c. And so we get sine 3e to the x plus c. And the next one that you tried, the function inside is tan x. The derivative of tan x is secant squared. So this becomes the integral sine u du. And this one, when you work backwards, will be negative. All right, and the last one I said we're going to have some fun with. I'm going to split my page in half, and I'm going to solve this one with 2 different techniques, and we're going to see something interesting with the answer. So, first of all, in this one, we can let u and du equal either one. In this case, I'm going to let u equal to sine 2x, because I know when I take the derivative of sine, I get positive cos. But I'm going to have, because I have a 2x, there would be a chain rule involved when there would be a chain rule involved when I take the derivative. So you'd have to multiply that by 2 afterwards. Did you see how I wanted to divide by 2? Well, because what am I doing from here to here? Taking the derivative, right? And so when I'm taking the derivative, this is the chain rule, which means after you take the derivative, you multiply by 2. Okay? Can you see where you're going to mess yourself up? Because we're taking the derivative in the middle of an integration question. And you've trained yourself well to do integration, which means you should divide by 2. And you've trained yourself well to do derivatives, and it's so easy to mix those up when you're doing one thing in the middle of another thing. So here, I'm taking the derivative. And the derivative of sine 2x is cos 2x, and then the chain rule means multiply by 2. So in order to do my substitution, I'm going to have to divide by 2, so I get just cos 2x dx. Now we can make our substitution. Where the sine 2x is, we can write u. Where the cos 2x is, we can write 1/2 du. That 1/2 can come out in front. And so we get 1/2 integral of u du. Add 1 to the exponent and divide by that number. Plus c. In other words, we'll get 1/4 sine 2x. Well, you okay if I write the squared like this? Sine squared 2x plus c. That's my final answer. That's method number 1 for solving this. Scroll back up to the top. Ooh, don't like this happening here. Here we go. Perfect. Just so you don't get confused. Method number 2, I'm going to use an identity. If 2 sine x cos x is equal to sine 2x. Do you remember that identity? Then what is sine 2x cos 2x equal to? Well, can you see when you have this and this, you have double it there? So if I have this and this, I'm going to have a sine 4x. But what am I missing out front? I'm missing a 2. So if I divide that by 2, it'll match up. If I do that to start with, then my original integral becomes 1/2 sine 4x dx instead. And this is an integral you do not have to use substitution for. Well, the 1/2 can come out in front. The integral of sine is cos, but it would be negative cos 4x. And because there would be a chain rule, I'd have to divide by 4 plus c. Now what's fascinating is when I simplify this, I get negative cos 4x all divided by 8 plus c. Total different looking answer than what we had started with. And it makes you think, is 1/4 sine squared 2x equal to negative cos 4x over 8? It might make you think that might be an identity. And I think I've graphed it, and it's not. So it really, in some ways, makes you feel like something went wrong. And yet with the plus c, no matter what values you put in, it still works out, just I think as a transformation of one and the other with different values of c. Yes? I can scroll up, sorry. But it's just a very interesting result that using one technique of integration and another technique of integration gives you different answers that aren't the same, but both are right. The main thing about integration with substitution that's going to help you is practice. So take the last 20 minutes, those questions at the bottom of the page, practice as many as you can. When I give you a review for this unit, there'll be a ton of integration problems that you need to do. Especially what's going to become helpful later on is when these ones are mixed in the middle of normal integration questions. So be not only able to do your regular integration, but also how do you get to the point where you can recognize that you need to use integration by substitution to solve for them.